So let's talk about nucleophilic substitution for a little bit. We should remember from organic lecture courses and from the pre-lab reading that there's two main types of nucleophilic substitution for alkyl substrates. There's bimolecular nucleophilic substitution, that's known as SN2, and there's unimolecular nucleophilic substitution, otherwise known as SN1. Now, the 2 and the 1 here refer to how many species are involved in the rate determining step or in the rate law for the reaction. So a bimolecular reaction involves both the nucleophile and the substrate in the rate law, whereas unimolecular substitution, the rate depends only on the substrate concentration and not on the nucleophile. Now, there's a lot of factors that affect the rate of an SN2 or an SN1 reaction. Things like substrate structure, identity of the nucleophile, concentration, temperature, as well as solvent. There's solvent effects in addition. For this experiment, we really just want to focus on 2 factors that are going to affect the rate of an SN2 reaction or the rate of an SN1 reaction. So we're going to look at 10 different substrates, which I've drawn here on the board, and we're going to compare them. And the main factor we're looking at is substrate structure. So some of these have a primary leaving group or a leaving group on a primary carbon. Some of them have a leaving group on a secondary carbon or a tertiary carbon. We've got allylic substrates, we've got benzylic substrates, and then just an sp2 hybridized substrate here. And we want to analyze the effects of these various substrate structure on the rate of an SN2 reaction or separately an SN1 reaction. And the other thing that we want to compare here is the identity of the leaving group. So you'll notice that in a couple of these, there's pairs of the same substrate structure, but a different leaving group. So bromine versus chlorine, one of these is a better leaving group than the other. And so we would expect that to have an effect, possibly a significant effect, on the rate of the reaction. And so we'll compare the rates of these kind of substrate pairs, the bromide versus the chloride. Here we've got cases for a primary substrate. Here's a case for a tertiary substrate. Here we've got a case for an allylic substrate. We've got the pairs there, and we want to compare the effect of leaving group on both the rate of their SN2 reactions and how they behave in SN1 reactions. Now, in an SN2 reaction, the way that we'll analyze this is we're going to use a nucleophile that will produce a precipitate after reacting so that we can identify when a reaction has occurred. And actually, we'll do this for both series. So in the SN2 reactions, we will use sodium iodide in acetone. In acetone, I-, so sodium iodide is soluble, even though it's an inorganic salt. It is soluble in acetone. You're left with the I- anion that acts as the nucleophile. But when this does a displacement reaction, let's say that it came here and kicked off the bromide ion is not soluble in acetone. And so sodium bromide then precipitates and gives you the indication that a reaction has occurred. Now, when we think about precipitates, often we think about something falling out of solution. In many cases, what we're looking for in lab is we're just looking for the solution to get cloudy, to get noticeably cloudy. That indicates that something is not soluble, even if it hasn't settled out of solution as a solid precipitate yet. So when we see that cloudiness, distinct cloudiness, that's when we can mark the time as a reaction having occurred. And so we'll analyze all 10 of these substrates using sodium iodide and acetone as the nucleophile, and then we'll add our substrates into that in a test tube, one at a time, in separate test tubes, and we'll look for a reaction response. We'll do the same type of process or analysis, but in an SN1 reaction case, using silver nitrate in ethanol. So in SN1, we'll use silver nitrate in ethanol. And in this case, the reason we've got silver nitrate here is so that when the leaving group leaves, which is the first step in an SN1 reaction, so if the leaving group leaves, it will form an insoluble silver salt, which will then form a precipitate, and we can see the presence of a reaction occurring. The nucleophile here, which is not involved in the rate determining step because it's an SN1 reaction and the rate determining step is just the leaving group leaving, but the nucleophile is actually just ethanol as the solvent. It's just a solvolysis reaction. And we've got silver nitrate just as our kind of label to indicate for us when a reaction has occurred. And so we'll go through, do these for all 10 of these substrates, and then we'll be able to compare the effect of substrate structure and, in certain cases, identity of the leaving group on the overall rates of the reaction. And we should know from kind of our background reading and from lecture, we should be able to predict what we expect to occur, which substrates we expect to react fastest, what effect substrate structure has on an SN2 reaction when the main objective here or the main issue at hand is how easy it is for the nucleophile to approach the carbon that has the leaving group on it. Versus in an SN1 reaction, we're no longer looking at how easy it is for the nucleophile to come in. We're looking at how easy is it for the leaving group to leave? What's the stability of the fragment that's left behind, the carbocation that's left behind if a leaving group leaves? And so that's what we'll be able to analyze here in this lab. So with that brief introduction, let's head up to lab and get things started and see what our results tell us about the effect of substrate structure and leaving group identity on the rates of nucleophilic substitution reactions. Here we are ready to begin the nucleophilic substitutions lab. We have a number of things on the card available to us for this experiment. First, we've got the 10 different substrates that we'll be using in this experiment. We have 1-bromobutane, 1-chlorobutane, 2-bromobutane, also known as sec-butyl bromide, 1-bromo-2-methylpropane, also known as isobutyl bromide. I have 2-bromo-2-methylpropane. This is tert-butyl bromide. And then I've got 2-chloro-2-methylpropane. This would be the tert-butyl chloride. I've got allyl bromide, allyl chloride, benzyl chloride, and then finally I have bromobenzene. These are the 10 substrates that we'll be using in the SN2 and SN1 analysis, looking at reaction rates. Now, to actually perform the reaction, the other reactant, depending on whether it's SN1 or SN2, I have those here. I have a 1 molar solution of sodium iodide and acetone. This will be for the SN2 portion. I have a 1% silver nitrate solution in ethanol. This will be for the SN1. And I have some extra ethanol, and I can use extra acetone from a wash bottle if needed. Now I'll actually perform the reaction in test tubes. So we've got 10 test tubes here in a test tube rack. And I've got various micropipettes to measure out the appropriate amounts of the various reagents. So for the SN1 portion of the lab, what I will do is I will measure out 500 microliters of the 1% silver nitrate solution in ethanol into a test tube. I will then add 100 microliters. So I'll take my micro pipette here and set it to 100. Now that's set to 100. I'll take 100 microliters of a substrate, and I will add that into the test tube. I'll put the syringe probably all the way down to the bottom, dispense, so that there's some mixing. And as soon as I dispense substrate, I'm going to start a timer and look for the formation of a precipitate. Look for the solution to get cloudy. Not necessarily a color change, because some of my substrates may be colored, but I'm looking for the formation of a precipitate. So it starts to get cloudy or stuff immediately crashes out. And I simply want to measure the time that it requires before a precipitate forms. Or for some of these, we will see that maybe no precipitate, maybe no reaction will occur within a 5-minute span. And so this will allow us to compare reaction rates across 10 different substrates. We'll do this 10 different times in 10 different test tubes for the SN1. Then we will clean out all of the test tubes carefully, and we will add 500 microliters of the 1 molar sodium iodide into a test tube. Add 100 microliters of a substrate and start the timer immediately upon addition. And then again, look for the formation of a precipitate. And we'll do that for all 10 substrates for the SN2 trial.